mention a little bit over the packet loss. Okay, so what happened when the packet loss is coupled with system call? Previous time we didn't explain. Okay, so you already know that the write system call during the connection, okay, will generate data, right? And when it generates data, it's basically give you immediate return, no matter it is acknowledged or not. Okay, so there's a sense that you can get by implementing the code, right? When you call write, immediately return, but you know it takes time for the ACK to come back. So it means that it don't bother whether the ACK is received, and you can keep saying write, okay, doing a while one loop, keep on writing, no problem. Now the problem is, let's imagine that what really happened in the network is a data loss. Okay, so this is not your application job to maintain the delivery, but the kernel's job to guarantee the delivery of that packet. Now the data packet want to be delivered, so you will have a timeout in the kernel side and have a retransmission. But look at the application side, nothing happened, right? Nothing, really nothing. Okay, and it will keep on letting you to write. Until then, until the ACK come back, it will reset the timer. Okay, so there's only a very subtle things. Okay, very subtle. It means the underlying thing will do it automatically. Okay, and if you're doing read, okay, you already know that doing read whenever a data is available, the read call won't block you and immediately return. And something that I want to tell you about, I guess you will have a experience doing assignment run, right? When you are trying to have an assignment one, read buffer is a 1K, and then 1K you can write 1K in the read call asks for 1K. Now here, let's imagine it is a 1K call. Now this data coming in is actually 12 bytes. What will happen? According to your experience in doing assignment one, what is the will it return? You write 1,000 here, 1K. But here, the data delivery here is only 12 bytes. It will report to you 12 bytes. Okay? So this is the reason. Okay? No matter what, okay, it will accumulate the data inside the kernel, and the time you call read, it will return to you the how can I explain? Let's say you want to have 1,000 bytes. If the kernel side has 1,000 bytes, it will give you 1,000 bytes. If the kernel side don't have 1,000 bytes, it will give the most data to you and give you the return value. Let's say there are 600 bytes and tell you 600. Okay, so this is the why here. Okay, and if of course if there's no packet delivered, let's say that the read call is here, so it's wait until here I get the data and send out the ACK and return. Okay, so now we go to have congestion. I never explained to you why we have congestion, right? Now this is a very simple view of what is congestion. And you don't need to afraid of it, okay? Because what? Because it's not your job to handle congestion. Whose job? Of course, is the kernel as well as the router. Okay? So what is congestion? Congestion is usually because of the router's feature. A router, usually we consider it as a store and forward router. So it's a mean of store and forward. You send something to the router store it, and look at the header, or you want to send from interface A to interface B, okay, I route it for you. Okay? And you know, when you look at a photo of a router, there are many plugs, many interfaces. So it's only from the left hand sending to the right hand. That's simple. But it incurs time. Okay? It needs time to find the correct interface to go out. So it has a buffer. It has a buffer to buffer those packets that it cannot process immediately. Okay, so we call it store and forward router. Okay, so imagine that this router sucks. Okay, only handle 1 segment per second. I never find a router like this. Okay, only 1 segment per second. Okay, now if the sender rate is the same as the router process rate, we don't have any problem, right? You will have the first second, this packet will transfer to here, and then it may eventually transfer to the receiver side, okay, and so on and so forth. Okay, so on and so forth. Okay, now what if under this scenario we are okay? How about I halve the transfer rate? How about half the transfer rate of this router, or processing rate of router, or I should say, always a producer-consumer problem. Okay, the producer, the sender, is having a higher rate than the consumer. The consumer, I will consider, is a router sending data out. When incoming rate is higher than outgoing rate, we will have a problem. Okay, the buffer become an important factor. If the buffer is big enough, no problem. We have let's say, 20 terabyte of memory, then no problem. I can always host every packet in a router and then let it process slowly but surely. I can deliver to the receiver side. Now, what will happen if I have this limited buffer, but the rate is being halved? Let's imagine that in a time equal to 1, I send a packet out, but it needs 2 seconds in order to process and send it out because it's 0.5 second, 0.5 per second. So at a time equal to 2, time equal to 1, I deliver it here. Time equal to 2, I deliver the second data to the router. Yet, it so happens it's time equal to 2, I can send the router's buffer packet to the receiver. Time equal to 3, we go for like this. Time equal to 4, the 2 will deliver to the receiver. Yes, the 4 packet will arrive at the router. Time equal to 4, time equal to 5, 6, 7. 7 has some problem now. All buffer space are used, okay? So happen that we don't have any problem yet because time equal to 8, we can process the 4th one. But how about we have the 9th packet? When time equal to 9, what will happen? Do you have any buffer space? No buffer space anymore. Okay. So what should you do? What should you do? Tell the sender to stop? No. Router don't have this feedback control. Okay. When we have the 9th packet, the 9th packet will be dropped by the router. We call it strategy of a router, call it drop tail strategy. Where the tails get full, the later coming packet will get dropped. Now imagine the router on CHK is doing this implementation and you are at the time at 8 o'clock p.m. on a certain day. You know why I said 8 o'clock p.m.? Yeah, kills us. Yeah. When it happens like that and the implement drop tail, no matter how hard you press your F5, do you have any effects? No. then you know why now, okay? It gets dropped by the router, not by the QSA server. Okay, of course QSA server also has this kind of implementation, right? It's also maintaining a queue. And when the queue is full, drop tail. Okay? I guess Patrick will also teach you another strategy. Okay, another strategy in implementing the router queue. Okay, later on let him to talk about it. There is a probabilistic way to early detecting the congestion. Now, imagine that the router has zero intelligence. It only knows how to drop tail, and this is why we have congestion. And of course, the TCP cannot sense this. Why I say the TCP cannot sense this? TCP is a protocol controlling the end host. Only the end host, the client, only the server will know about the congestion by looking at timeout. And in a router, there is no feedback control, so we have some problem. Okay? And of course, we have some false positive results. So what is the positive result? Well, the positive result is the timer on the TCP sender side is not long enough. And if that false positive implementation is all over the world. Imagine. All over your computer used to connect to users. They all have false positive. They should wait longer. Let's say the timer should be set to 1 minute, then users will give you a reply. Okay? But no, your TCP timer is way shorter than 1 minute. Then you are actually generating more and more packets, right? You do the retransmission, right? You do the retransmission, and that's why it will complicate the story. And you know, that's why we say that the congestion is a bad thing, really bad. And how bad it is? How bad it is? Imagine this router is always have a processing rate of x/2, and this is an approximated result. For the first wave, you have a very high probability to drop off half of the packet. And then that's why you need a second wave of retransmission. And the second wave of retransmission also has a chance of dropping half. Then this half will also drop half of it. And at the end, you approximately need 2 amps. That means that you have a 1 gigabyte of data to send, but the router is not fast enough. And the difference in the sending rate and the processing rate is like this, 1/2 of ratio. Then you need double the size. Okay? And if the internet is in this implementation, we will have a big trouble. Okay? How big it is? Okay? We have a statement. Okay? The inventor of the congestion control called Van Jacobson. Okay? This is a great man in a computer science and networking. Okay? His statement is, if you don't control congestion, let it retransmit. You are pouring gasoline onto the fire. Okay? You use gasoline to put off fire. Can you do it? No. It becomes a bigger fire. Okay? And in my time, okay, in my time we have you know, I know the secondary school now don't have this passage. Okay? Okay? 有啊 A level has. I mean not A level. Current DSE have. It's removed. 有啊 some school choose it. Okay? Then you understand what this statement means. You are holding the woods and go into the fire and try to put out fire. Of course, you will die more fast. Okay? And in the next time, we will understand what exactly or how we can derive a correct timeout period. And this is a research work from Van Jacobson. And next time I will also introduce you what is how Van Jacobson is look like. Okay, he's a fat guy. Okay, inventing many rules like the trace route, something like that. Okay, so